Now, one more example of the same type. So still it is a competition between two species. And the question is the same. Are the species going to coexist, or one of them is going to disappear? And note the following coefficients, that the coefficient here at xy in the first equation as compared to the same coefficient at xy in the first equation became smaller, but the coefficient at xy in the second equation as compared to the previous example is exactly the same. Which means that if we compare with the previous example, the bad influence of x on y remains the same, but the bad influence on of y on x is reduced. So, which means that for x the competition became easier, and for y the competition is still very tough. So let us see if it is going to help x to win the competition between the two species. So now what we expect is that if there is an equilibrium point, then maybe at least the population of x is going to be larger and the population of y is probably going to be smaller. But it is in fact even funnier. It is still a linear system, but the answer is that the population of x is just negative. So which kind of doesn't make any sense at first. So I suggest that you pause the lecture and try to figure out what it means. But as a matter of fact, it just means the following. It means that this is not a meaningful solution, so it shouldn't be taken into account at all. We just ignore it. So we just don't bother about it. So instead, we should look at existing solutions, of which there are 3. So now there are 3 meaningful solutions: 0, 0, when x is 0 and y is at carrying capacity, or when x is at its carrying capacity and y is 0. And, well, as you see from the plot, just as we expected, the population corresponding to the case when x is at its carrying capacity seems to be a stable critical point. But let us calculate it theoretically. So here is the Jacobian matrix, and again, when x is at its carrying capacity and y is 0, and notice that we don't even need to really calculate it, because both, this is an upper triangular matrix, so the both eigenvalues are negative, so it is a stable node. But then the similar case, but when x is 0 and y is at its carrying capacity, this is a lower triangular matrix. It doesn't matter, so still the eigenvalues are just elements on the diagonal, one of them positive, another one negative, so it is a stable point, which means it is unstable. So what it tells us is that the species y is always going to die out in the presence of species x. Even just a little bit of population of x is there, then x are going to win the competition. So let us summarize. So two competing species can be described by a system of these quadratic differential equations. There are 4 equilibrium solutions, typically. Let's say there are exceptions that I don't want to go through, but typically there are 4. The interesting one is when both components or both entries are non-zero. But what we just saw is that if the competition coefficients are small, then there is going to be coexistence and asymptotically stable equilibrium with both species present. So if one of the coefficients is small and the other one is sufficiently large, which I do not quantify, although it can be done, then one of the species is going to die out. And if both of them are large, then one of the species is going to win the competition depending on the initial condition. So note that in all the cases, yeah, in this case, the equilibrium where one of the population is this equilibrium with non-zero populations actually doesn't exist, meaning that either x0 is going to be negative or y0 is going to be negative. So it is kind of, it's not a real one. But anyway, so far in all these cases, a stable equilibrium was always when at least one of the two species is present. So is it possible that the competition is so bad that both species disappear?